Rightio. All right. Well, welcome back again after holidays. So recording this session as per normal. So yeah, later on in today's session we'll be covering steel in commercial construction. So well, multi-residential construction, but that flows very much into commercial construction. So we're talking heavy gauge stuff and some light gauge steel framing as well. But before that, we'll also touch on fire resistant construction. So dwellings that are multi-residential dwellings through to all sorts of commercial dwellings have requirements to have fire separation. So if we have a fire that happens in one unit, that fire doesn't spread to neighbouring units, or at least gives the occupants of neighbouring units the time to evacuate from their units safely. So we have fire resistance levels. Those fire resistance levels are typically expressed in these figures that we see here, 90, 90, 90. That relates to minutes. So it means that a certain wall or certain building element has to be resistant to fire for 90 minutes. That's so the NCC stipulates this is how long it has to be.
90 minutes is what is it? About the time of all burning out the world.
Yes. So these different numbers, the reason we have 3 of them is our first 90 relates to structural adequacy. So the wall has to stand up for 90 minutes. If the wall is standing up for 90 minutes, then it passes. It has to maintain its integrity for 90 minutes. Integrity means it has to stop the passage of flame from one side of the wall to the other side of the wall for 90 minutes. So it may be standing up, but if it gets a hole in it within that 90 minutes, well then it fails. So it has to stand up for 90 minutes, it has to maintain its integrity for 90 minutes, and then it also has to maintain its insulation for 90 minutes. Sometimes within the NCC we have our fire resistance levels expressed as dash 90, 90. That dash means there's no requirement for it to maintain its structural integrity. Those levels we have expressed when it's a non-load bearing wall. So for a load bearing wall, it has to maintain its structural integrity. For a non-load bearing wall, it doesn't. So it'll still stand up, but it's not taking any weight. So it doesn't have to maintain it, but it still has to maintain its integrity, so it can't have flame passing through it, and it still has to maintain its insulation for that time. Now, not all fire resistant levels are 90 minutes or 1.5 hours. Some of them are only 30 minutes, some of them are 60 minutes, some of them are 3 hours. It all depends on the situation of that building element. Now, the way we find out that situation of the building element, we have to go to the National Construction Code for doing that. So to go to the National Construction Code, everybody should have been here already now, so you should have created your own login. So we go to the Australian Building Codes Board, or ABCB, type that into Google, that's the first thing you're going to come up with. Save it to your favourites bar, and then this one, that's our login. So I'll just put my login details here. So there we go, I'm all logged in, and then once logged in, I've got access to the National Construction Code suite, so the NCC suite. Now, as you probably know, the NCC comes in 3 parts. Volume 1 for commercial construction, so classes 2 to 9. Volume 2 is for classes 1 and 10. That's our detached residential and garages and carports for class 10. And then volume 3, that's predominantly for plumbing and drainage. So being a class 2 dwelling, we're looking at a multi-residential dwelling for our project number 2. So we're concerned with NCC volume 1. So we open that up, two different options here. One, you can view it, one you can download the PDF. So if you're going to be using your computer at home predominantly, might as well just download the PDF and have it sitting there. Or if like me, you're in this situation, you can just click on view. Do beware that if you go to download PDF, it looks slightly different than if you click on view. So yeah,
Maybe just a view is less information than PDF file.
Yes, it navigates slightly differently. So I'll show you. So if we click on view, this is what it looks like. We have our bar down the side here with our contents, and then we click on, say, structural provisions, for example. It brings up only that page that I've clicked on. If I go back to NCC Volume 1 and I go to download, it'll take a little while to do that. I still have the contents here on this side, and we'll go to section B once again, structural provisions. There we go, it brings up structural provisions, but I can just keep scrolling through the whole document. So I have the whole document there in front of me. Either way, but you'll see that the navigation here on this side looks a bit different than it does in the other version. If we go to just view, it's a much simpler contents page on the side here. I find it actually a little bit easier to read myself. Anyhow, so what we want to do first up is go section A for general provisions, and we're interested in classification of buildings and structures. Now, it's probably no surprise here that our second building that we're doing is a Class 2 building. So a building containing 2 or more sole occupancy units, each having a separate dwelling. That sounds very much like the building for project number 2. So we've got four units in a block of 2 units. So we have a look at Class 2. Then we want to know what fire resisting construction it requires, because we have to specify that. So for doing that, then we go to section C, fire resistance. So click on section C, fire resistance, and let's expand that out. Part C1, fire resistance and stability. So we'll have a look at that. As soon as we click on part C1, it takes us to type of construction required. Fantastic, that's what we needed to know. We get this table up in front of us. So table C1.1, type of construction required. Class 2 building, 2 stories, we're type B construction. Yeah, but what does that type B construction, why is that different from type A and type C? Well, in a nutshell, if we look at this for our class 2, 3 or 9 buildings, if it's only 1 story, it's construction type C, and if it's 3 stories or 4 stories, then it's construction type A. From that, we can simply gather that, okay, A is for higher risk construction. So that's for when we've got a taller building with probably more people living there. The fire resistance requirements are probably going to be more stringent for that. Whereas if it's only 1 story, it's not a very tall building, we won't have many people living there, the fire resistance doesn't have to be as stringent because we've got less people to evacuate, etc. in that scenario. So for your fire resistance, you've got type C, type B and type A construction. Type C is the less onerous, type B is somewhere in the middle, and type A is the most stringent. But to know how stringent it is, etc., we go to this section here, specification C1.1. So it says each building element must comply with specification C1.1. Okay, well let's have a look at specification C1.1. So here we are at specification C1.1. Now that sits in a different section of the NCC to our fire resistance. Well, it's underneath, right? So we've got fire resistance and stability, but we can just use that hyperlink. But if we want to go back there, we can just click on fire resisting construction. But now that we know that we're type B construction, the thing to do is have a read through this, our general requirements. So we go through looking at our general requirements. But to shortcut the process for you, I'm going to scoot down through to show you that what we have happening. Sorry, I took you too far on the side bit there. So C1.1, so we read through this, and then we get to type A fire resisting construction. Okay, we've already determined that's not us, so we keep scrolling through. Keep going. Oh, here we go, type B fire resisting construction. That's going to be relevant to us. And I'll make that slightly larger as well so we can read it a bit easier on the screen. So, type B fire resisting construction. Certainly have a read through all of this. There are elements in here that are going to be relevant to the building, but the most relevant is this table here, type B construction FRL of building elements. And here we have those numbers that I referred to before as our fire resistance levels. So structural adequacy, integrity, and insulation. So for any external any external wall, for load-bearing parts, less than 1.5 meters from a fire source, it has to stand up for 90 minutes, has to have not any holes in it for 90 minutes, and it has to provide insulation for 90 minutes. That's if it's a class 2. Now, if we were to change that building to an office, so an office block, then all of a sudden we're class 5. To be able to change it to a class 5, we would have to change the walls or increase the fire resistance levels of those walls, possibly. If it was all tilt-up concrete, well then we're fine. But if not, then we'd need to upgrade the walls. If it was a class 6, which is a retail showroom, etc., then we have to increase it once again to, what is that, 180? That's 3 hours. If we were to make it a, can't think of it off the top of my head, 7B, but if you have to make it a 7B or 8, then it has to be 4 hours fire resisting construction. So, so we've determined our fire resistance levels for various different building elements. Then we've got our load-bearing walls within 1.5 meters of a fire source, 1.5 to 3 meters of a fire source has to be this, 3 to 9 has to be this, 9 to less than 18 has to be this, and 18 meters or more doesn't need any fire resisting construction. But what do we consider to be a fire source feature? Well, a fire source feature is, typically a fire source feature is another building. So the reason another building is a fire source feature is because we don't know if and when a building is going to catch a light. So a building might have a fire in it, and we want to stop that fire getting to our building. That's what this is all about. So if we have another building on our block, on our own allotment, like a shed or something like that, that shed is classified as a fire source feature. So if we've got some walls, 3 to 9 meters away from that fire source feature, then they have to have that fire resistance level. But if we don't have any other buildings on our allotment and don't plan to build any other buildings on our allotment, we still need to pay attention to this if our building is within 3 to 9 meters or 9 to 18, etc., of a boundary. The reason we need to consider the boundary of the allotment as a fire source feature is we don't know if the next door neighbours in the future are going to build a house right on the boundary. They may do that. They may demolish and then build a house right on the boundary. So in terms of assessment, we always have to assess these in context of how close we are to a boundary or to a fire source feature. So it could be another building. It could also be parked cars. So if we've got car parking underneath a building or right next to a building, that can also be a fire source feature. So that's the way that we work out those fire resistance levels. Now you'll notice that it covers external walls, external columns, internal walls, and then other load-bearing internal walls and columns, and then for roofs it's got nothing. The reason that it has nothing for roofs is because further up here, well, it's further on in the NCC before we get to Type B construction. It says that any fire-resisting wall has to carry all the way to the underside of a roof. So that wall between two units has to be carried all the way to a roof. That means that if a unit catches a light, then that roof can burn out, and the fire service can be pouring water in there, etc. But that won't cause a fire to spread to the other units because the walls carry all the way to the roof. And so, for that reason, roofs don't need to be have a fire resistance. But what about when we have several units on top of each other? What we don't want happening is a fire in one unit down below, and then that burning the unit above it, which burns the unit above it. We want to stop that spread of fire. Now, these tables don't cover ceilings and floors, but what does cover that is this section here. So in a class 2 or 3 building, except where within one sole occupancy unit or a 9A healthcare building, or etc., a floor separating stories or above a space for the accommodation of motor vehicles. So a floor separating stories, so that's one unit to another, or above a space for accommodation of motor vehicles or used for storage of any other ancillary purpose, must be constructed so that it at least of the standard achieved by a floor ceiling system incorporated ceiling which has a fire resistance to the incipient spread of fire to the space above itself not less than 60 minutes, or have a fire resistance level of at least 30-30-30. So it has to stop the spread of fire for half an hour. Or have a fire protective covering on the underside of the floor, including beams incorporated in it, if the floor is combustible or of metal, and etc. That's where we might as well stop for the purposes of our assignment. So any floor materials within your task 2, your project 2, have to have a fire resistance level of at least 30 minutes, or if they are of combustible construction or metal construction, then they have to have a non-combustible coating covering on them, so fibre cement sheet or something like that, something that's non-combustible. And that's it. That's how we go determining the fire resistance levels for any building element within a group of units. I'll just pause that for a minute. Larger, there we go. Yeah. So that covers our first section that we're going to go through tonight, is determining the fire resistance levels of various different building components and how we go about it. Now that same process, well, that process is going to be the same whether we're doing a small multi-residential development or a major commercial development. It's just the answers will be different. So we'll take that same approach of classifying the building first, then going to table C1.1 to determine the type of construction required, and then once we know the type of construction required, then look at the fire resistance levels for the various different building elements. Now, to make those building elements resistant to the incipient spread of fire, there are several ways we can go about it. One is we can just build everything in concrete. We can do concrete panels and have no penetrations through those concrete panels, or any penetrations that we do have fire stops on them, etc. And we can just do the whole thing in concrete, and then you're not going to burn it down. It's going to easily meet those fire resistance levels. But from an economic standpoint, and also from a human occupation standpoint of buildings, we don't just build everything out of concrete. So one thing that's good in terms of building buildings cheap is by using light gauge steel framing or light gauge timber framing. But to make that light gauge framing cheap enough to build with the fire resistance levels, the way that's achieved is with fire resistant plasterboard and insulation. Now, to do that, we go up to here. To do that, we'll refer to the CSR website. Now, this is not to promote any particular product over another, but just their product literature is fairly good, and that's basically how things go. The product manufacturers that have really good product literature that's really easy for designers to use, designers typically use it and specify their products. It's sort of part of it. Anyhow, so multi-residential fire solutions. So first thing they've got mentioned here is Gyprock Fire Check and Gyprock Fire Check MR. So these are plasterboard products. So plasterboard, that's this stuff here. It's a sheet of paper, and then gypsum plaster, and then another sheet of paper in a sandwich like that you can paint it, you can screw it. It is relatively rigid, but just your standard plasterboard doesn't react very well to severe impacts. If I was to run my chair into it really hard, I'd break it, etc. Anyhow, for use within buildings, we have various different types of plasterboard that we require. So there's fire-resistant plasterboard for creating fire separation between elements. There's moisture-resistant plasterboard for using plasterboard in wet areas, because wet areas require moisture-resistant linings, or what is it called? Water-resistant linings. There's Gyprock Eco 8, so that's a Gyprock which uses some recycled component within it. And then Gyprock Shaft Liner, that's for lift shafts and things like that. So it's a very rigid, strong, thick plasterboard for a shaft liner. And then there's some good information in here. Talks about FRLs once again, and gives a bit of a summary of Type A construction from the NCC. But because we know how to get the specific information ourselves, that's not of too much concern. But what is fantastic, a very good guide for you to get, is the Red Book. So get this yourself and keep this yourself at home on your computers. If we click on that, it takes us to this. Where do we go from here to download? Download the Red Book, and then we fill out all these sections and we download it. In regards to that, here's one I prepared earlier. So this is my copy on a USB. It is a massive document because it covers so many situations. One of these situations I prepared just before the class, or scrolled down to, is they have a series of tables that show various different forms of construction. Here we have a form of construction with staggered studs. So that's that's a thick, you'll notice a very wide bottom plate, and then studs offset. So one stud one side like this, and then the insulation snakes through between those two studs. That enables a continuous line of insulation between the two. So this stud is insulated from this wall, that stud is insulated from this wall. And then with that staggered stud construction, using fire check plasterboard, one layer of that on either side gives you an FRL of 30, 30, 30 for both sides. Or we can go down further, have two layers of fire check on either side, gives you 120, 120, 120. So 2 hours of fire protection. So that the addition of another layer increases the fire resistance exponentially. When you construct any of these walls, so within this document, because it's really large, it also covers lots of installation details, etc., just to make it simpler for you. When you install this plasterboard, you have to stagger your joints. So you don't have joint on top of joint, because then fire can just, once that joint opens up, fire can just pass straight through there. So where you have a joint, then you lap your sheets over that, and you have your joint midway between the other joints. I can show you that later. But and then within these details, they've got this red for simple fire check and this blue for moisture resistant fire check. Has the same properties for fire resistance, but moisture resistant, that can be used in a bathroom. And so produces 120 minutes of fire resistance, etc. And then if we go down, so these are double stud systems. So we were looking at staggered studs before. These are double stud systems, etc., etc. So those tables give you some fire resistance levels for your various different situations. But then within those, beyond those details, then we get installation details such as this. So it shows how that fire check has to be installed to meet those fire resistance levels. So here we can see the staggering of joints, etc., and then the spacing of fixings. So all the walls have to be, all the wall sections have to be installed as per those details. So it's an incredibly handy guide to have. Other things included in this guide are an explanation of the various different types of plasterboard available. So there's plasterboard plus, just plus, I guess they called it plus because they didn't have another name and they wanted to make it sound good. That's just standard 10mm plasterboard. Super seal, that's plasterboard for ceilings. The reason plasterboard for ceilings is different than plasterboard for walls is because our loads are different. Ceiling, it hangs from joist to joist, and it has to be more rigid, otherwise it will sag between the joists. AquaCheck, that's plasterboard for, what's that? Yeah, waterproof. Yeah, waterproof plasterboard, or moisture resistant, water resistant plasterboard. So no plasterboard is waterproof. You won't make a water tank out of plasterboard. It will, eventually, yeah. But it's water resistant. Sound check, that's sound resistant or sound attenuating plasterboard. So it soaks up sound, doesn't reflect sound to the same degree. Sensitive gyprock. So that's for people with various different allergies and sensitivities to aspects within plasterboard. Super check. So that one is clearly noticeable reduction in perceived loudness compared to standard plasterboard, and has a will span 600mm in ceiling applications. That's pretty standard. Double the force to impose a discernible surface indentation compared to standard plasterboard. So it's a little bit stronger. You can whack it, so it's a little bit stronger, and then also has some sound attenuation capabilities. And then beyond that, then we're getting into well, we've got standard plasterboard. Oh, where did that other go? But yeah, we've got various different forms of plasterboard there. And we've got plasterboard like flex or gyprock flexible. That's a thin sheet of plasterboard. So this is only 6.5 millimeters thick in comparison to our sharp liner, which is 25 millimeters thick. This 6.5 millimeters thick means you can bend it, and you can wet it down slightly and increase its bending capability. Shaft liner panel, so it's a very thick, strong plasterboard for lining shafts. And Eco 8 Complete, that's sensitive with recycled components. Eco 8 Moisture Resistant, so recycled plasterboard with moisture resistance. Fire Check, we sort of jumped over the page there. I lost it again. Great. So Fire Check Moisture Resistant, so where you have to have fire separation walls in a bathroom situation. Fire Check for fire separation. Impact Check, that's for hallways and things like that for disabled access, because you've got wheelchairs and things like that that bang into those walls. And Sound Check, Aqua Check, etc. So that's the red book. So it covers your different types of plasterboards, but then we've also got our different plasterboard products and things like that, various different hangers and whatnot to stop. That one's for stopping the transmission of sound, so that's an isolating mount for that. Various different information on installation and various and other products, etc. Shows you how to do a curved wall, for example. Rondo is owned by CSR as well, so Rondo produce light gauge steel framing members, and so you'll see within the red book they refer to Rondo Rondo steel wall components as well, but then various different installation details, etc. as we go through. So refer to those as necessary, but plenty of fantastic details in here of exactly how you will achieve various different scenarios. All right, so that's the red book. Close all tabs. So that's how we go achieving those fire resistance levels. Another way of achieving fire resistance is also using Hebel. So that's autoclave aerated concrete. And so they've got their various different details for intertenancy and party walls. So that's walls that have to have fire resistance to stop the spread of fire from unit to unit. So they've got their various different systems, and a summary of those systems is here. So power panel, 75mm plain panel, provides 90 minutes of adequacy, integrity, and insulation. But then a 50mm panel with 70mm stud frame will do the same thing, and then a 50mm panel with a 90mm stud frame will do the same thing as well. We'll have a quick look at this table here. So here we go. Our different walling systems, their thicknesses and the FRLs, and the required insulation for those. So you've got that information there. But then also further down in your downloads, you've got CAD details. So here with power panel for low-rise, multi-residential, etc. So yeah, so intertenancy wall details and external wall details. So they like to make that really easy for you to use their products. As a designer, you can go, oh yeah, I want to download that CAD detail, keep that one in my blocks library for specifying these intertenancy walls. And another thing, we won't go to what builders think. You- I imagine on the Hebel site, they're just going to go, "Oh, Hebel's fantastic. I use it all the time. Thank you very much." And that, that may well be the case. But this video here, I think, is a fairly handy one. So we'll have a quick look at that one because it just shows you how it goes in. So in what context it's used. Yeah, just got that last little bit. So as I mentioned before, all the fire separating walls have to carry all the way up to the underside of the roof. So it's not just the internal walls, but we have to go up into the roof cavity, and that's where they're going now with this. So they're going up into the roof cavity there. Yep. So that gives you some idea of the components and the context, etc. So yeah, plenty of details there as well. So certainly there are other ways of producing fire-resisting construction internal walls, other ways of using concrete blocks, masonry, solid concrete, etc. But for your cheaper options that use lightweight framing, etc., these are a couple good examples of that. So we'll get on to floor trusses and roof trusses possibly if we've got enough time. But the more important thing to have a look at tonight is now the steel construction. So with that steel construction, you've got typically two classifications of it. You've got your hot rolled, which is your heavy gauge steel, or your really like universal beams, equal angles, parallel flange channels, etc. And then your cold rolled sections. So that's any steel that's a thinner gauge that comes from a roll of coil steel that's rolled out and cut and bent into various different shapes. So a lot of your Stratco sheds and things like that, all their framing members are cold rolled steel. So it's thinner gauge rolled into a C section or a Z section, whereas your hot rolled, that's all your much heavier steel. For your hot rolled stuff, most common, so people call them I-beams. Correctly, well, how to say it, within the product literature known as universal beams. and you've got both universal beams and universal columns. The difference between a universal beam and a universal column is with a universal beam, this web depth is it's a longer dimension than web depth is a longer dimension than your flanges, either top and bottom flange, and this is your web here. Universal beam, it's much deeper. For universal column, do we have a universal column? No, we don't have any UCs here. What's that? With a universal column, our flanges are the same width as our web, so very square in cross section. So, and those universal beams are referred to as by their depth here. So, for example, if we've got a 310 deep universal beam, it's known as a 310 UB. But those 310 UBs also come in various different weights and thicknesses of our flange and our webs. So we might have a 310 57 UB, which means that it's 57 kilograms per lineal meter. Or we might have a 49 310 UB, 49 kilograms per lineal meter. Those different weights, they also impact on the strength of that universal beam. So a 49 UB is going to be weaker than a 57 UB, for example. Another very useful section in steel framing is a parallel flange channel, or a PFC. That's a hot rolled C channel, used a lot in things like retaining walls, etc. But there are also TFCs as well, which is a tapered flange channel. So here we've got our channels that are both, our flanges, which are both exactly parallel and flat, with a tapered flange channel, that these bits have a taper on them and they get thinner as we get closer to the edge. So we might use those, for example, if we've got to be slotting things into them, for example, or if a lot of the strength has to be around the web as opposed to the strength in the flanges. Yeah. Have you encountered those?
Oh, I haven't seen TFC. What is TFC?
So a TFC, that's a tapered flange channel. What I'll do is I'll get the One Steel catalogue open as well. Dual screen would be handy, I guess. Let's have a look and see what diagrams we've got to see any. Okay, there's not a great deal of pictures. There's some pictures associated with the tables. These are welded beams, universal beams, universal columns. So as I spoke before, universal beams are more of an I configuration. Universal columns are more of an H type configuration. That's our tapered flange beam. So it's like a universal beam, except our flanges taper. They get thinner toward the outside. And then that's our parallel flange channel. So they're the same. We don't have any tapered flange channels in here for One Steel. Yeah. Okay. Well, I'll move on from those. Oh, go to the other one. So, and then our angles. So angles are used a lot in this hot rolled steel framing as well. Like Tonsley is a fantastic place to seal these elements in use. You know, if we look out the window here, we've got universal beams, we've got equal angles welded on as well. So that this great big column here, dead legs in there. That's two PFCs welded together to create a column. So this is our weld up here. So there's, what do you call that? Full penetration butt weld, is it?
Yeah, if they do.
Was that?
If they do full penetration, there is full penetration.
Yeah, we can't tell that from. We'd have to cut it in half to find out.
So, is it welded all the way along?
Yeah, welded all the way up.
Is it produced by like a one steel or just somebody did it?
It would have been done by one steel, I'm pretty sure.
Yeah.
Yeah, for major constructions like this, you wouldn't be doing this on site. Right, so you'd be manufacturing these elsewhere.
Probably full penetration.
Yeah. But then, as we look around, look outside the window, our balustrade there is made of flat bar with flat bar tops. Look across there, we've got these columns that are created by universal beams with equal angles as webs, and some flat bars in there is for web. Actually, no, they're equal angles as well. Looking at the roof, we've got SHSs and equal angles and some unequal angles and some flat plate for cleats, etc. So Tonsley is a fantastic place to see all these bits in use. But for those at home, just I guess either come into Tonsley and have a look around or have a look online at various different uses. But our angles, we've got both equal angles where both of our flanges are exactly the same length. So a 50 equal angle, each flange will be 50 millimeters long. With unequal angles, this one may be 50 millimeters, that one may be 90 millimeters, for example. So we've got various different dimensions of unequal angles and then equal angles. The reason why we would use an unequal angle is where we need more strength in this vertical direction than we do in the horizontal direction. We use an equal angle when we require strength, where we've got equal forces from both directions or from any direction acting upon that. Another very handy steel section for large span steel framing, portal framing, for example, are SHSs, so square hollow sections. You'll see a great deal of portal frames made out of square hollow sections, and we've got, if once again we look out the window here, we've got this grid system over there supporting the windows to the workshop. They're all square hollow sections with cleats on the end of those. Any idea what a CHS is? It's got another name as well that you probably know it by. What could C mean? Any ideas? Yeah, so it's a circular hollow section. So it's a pipe or a tube. So, which is, so a steel pipe basically. But steel tube gets used in structural aspects as well when we've got equal forces coming from around as well. Then RHS, as you mentioned earlier, RHS is a word which is used for just about everything, but it actually refers to rectangular hollow sections. So when it's deeper than it is wider, then it's a rectangle. Or when the cross section is of a rectangular shape, then it's an RHS. So often used as beams, particularly in relatively small or external construction, where animals can't sit on them, as on I-beams. So these steel members are typically joined together by cleats, which enables the manufacture of this to happen in a factory or in a steel workshop, and then it can be sent off to be hot dip galved. So that way we're not having to weld bits and pieces on site, because sometimes many of these components, if we were to join them all together in a factory, they'll be way too big to send for hot dip galvanizing, but then also too big to transport on a truck to get installed. So they have to be installed in pieces on site. They have to be galvanized in pieces in the factory. So so you've got various different jointing mechanisms, and a cleat is a really common way of joining these steel sections. Another way of joining them is with flat plates. So it's like a cleat, but it's instead of welded onto the side of a member, it's welded onto the base or the top of a member. This is a really common detail for portal frame construction. So our portal frame construction, that's where we've got a rigid frame that, I'll say it, that carries all the bracing load and the spanning capabilities of of the structure. So it's a frame that works together in its own individual, well, a frame that works in as a single unit, going from one side to the other. So this is a very common detail for that. The reason this is really common is that it enables adjustment of the height of that base plate. So for the installation of this, we have these threaded rods which are cast into the concrete footings, and then nuts screwed onto the top of those threaded rods. Then the portal frames are put on top of that, and then the nuts are put on top, and that enables some adjustment from underneath. So you can lift it up and pull it down to get everything exactly level and in place. Also, these holes in our flat plate might be slightly larger than the holes than the diameter of our threaded rod, to enable some minor sideways adjustment. But the best case scenario is that these threaded rods are placed very accurately during the concrete footing pour. So things such as wall trusses. So if we look around the structure of this building here, we'll see trusses and all sorts of sections made out of these various different hot rolled sections. So here we've got a what do we call it? Like a parapet wall truss that's enclosing one end. So that's our hot rolled sections, but also in a lot of commercial construction, and right here we've got cold rolled steel sections as well. So within this wall, this is probably not going to be a timber frame wall. I imagine this is going to be that light gauge steel framing wall. Light gauge steel framing is made, as I said before, from coil steel that's cut into sections and then folded into various different shapes for various different properties. So we've got top hat sections and furring channels. The difference between a furring channel, the difference between a top hat and a furring channel is furring channels are used for battening out where we've got an existing wall already. So we've got, say, a masonry wall that we want to attach some plasterboard to. We'll attach furring channels to that, which are like a top hat, except they slope more. So they're easier for fixing, but they can slope like that because they don't need to be very strong. So because we fix them to a masonry wall or some solid structure already, they don't actually need to be very strong. They just have to hold that plasterboard. They have to be something to fix to. That's it. So furring channels, slightly different shape and less rigid in their construction, whereas top hat sections, they get used for fixing plasterboard to in ceilings and various other battening out of non-solid walls where they have to span a distance, so they're slightly stronger. The reason they're called top hat sections is because if you were to cut through them and look at the end of them, they look like a top hat. So typical sizes, 35 millimeters, 50 millimeters, etc. We also got Z sections and C sections. So C sections, they're very common. You see a lot of those. They're shaped like the letter C. Have either of you ever seen a Z section before? So I don't know if we've got got an image here of a Z section. Oh, there we go. There, we've got a Z section and a C section just here. So if we're doing some purlins on a roof, we can do a C section or a Z section, But why, as a builder, why would I prefer to use a Z section rather than a C section?
Easy to put the
Exactly. Yeah, exactly. With our C section, yes, you can. If you long tech bit on your drill, you can get a tech screw through here, but it's going to be on a slight angle. With your Z sections, you go straight down. You're going to get better fixing. What you'll want to do though is ensure that you fix with your Z bit facing down, because if any water makes its way in there, you want the water to go off your purlin. You don't want it to be, if we did our Z the other way, then the water will pool inside there against our framing member. And also the same for wall girts. So on our roof, between our rafters, we've got purlins. The same bits of steel on the walls that go between our portal frames, they're called wall girts. So girts on walls, purlins on the roof. Also, can either of you tell me about the difference between a purlin and a batten? A roof purlin and a roof batten. A roof purlin is when it's standing up like this, when the section, so as to look at my phone here, for example, or for those at home, so when we've got our C section standing up like this, it's as a purlin. If we were to lay that C section down flat, then it's known as a batten. So on the flat, it's a batten. On the side, it's known as a purlin. So within this piece of construction here, we've got a whole mix of hot rolled sections and cold rolled sections. Can I get some identification of these various different things from you? What can we see in there?
color is different.
What's that?
Color is different.
Oh yes, our hot rolled sections are painted in rust inhibitor, the red rust inhibitor. But of our various different pieces, we've got some SHS here, some square hollow section there, and some SHS here. Up here, we've got an I-beam, or universal beam, sorry. Here, we've got a flat plate cleat, going to another cleat with our bracing, which is our rod, so it's a steel rod. Then up here, we've got SHS, once again, this one SHS or RHS, I don't know whether that's rectangular or square. So that's, pretty much it for our hot rolled sections. But then we've got a whole heap of cold rolled sections filling in the next part. So our hot rolled has been painted in rust inhibitor. These ones have got a zinc aluminum coating to them. So this started out life as coil steel and then got cut up and folded into various different shapes for use in here. So we've got some top hat sections here. We've got some, I think these are C sections here. Yeah, C sections there. Don't see any Z purlins in that. So there's the Lysart referee for various different C and Z sections. Also the Rondo guide for for various light gauge steel framing. But there's a whole lot of you've also got Stratco that produce various different steel sections as well, light gauge steel sections, and various other light gauge steel frame manufacturers producing either complete house frames or components of house frames as well. So mentioned Rondo. Now Rondo is a name which is fairly synonymous with ceilings. They don't only do light gauge steel framing for ceilings, but they're certainly synonymous with ceilings. They do these suspended ceiling systems. So within the TAFE here, they decided not to put the ceilings in. So the students can look up here and go, oh yeah, there's a floor trap there with, or a gully with several, wastewater pipes going into it, then to a 100 mil outlet, and etc. etc. So you can So as a lecturer, I can be talking about plumbing and go, oh look, this is what it's doing, or I can be talking about cable trays and go, here's a cable tray here, and it's got this in it, etc. So we don't have those suspended ceilings in here, but for a lot of offices, etc. Or I think either of you, have you seen these suspended ceilings before? Those grid type ceilings, where you've got ceiling tiles that you can push up and slide sideways. So yeah, so the old TAFE building we used to be in had those suspended ceilings in them like that. That's created by a series of, like, we've got C channels here that mount to the bottom side of a floor. Basically what they do is they just provide a fixing point for our hangers. So those hangers have to fix to something. So an easy way of doing it is with a C channel. Then those hangers are connected to these ceiling sections that are installed in a grid fashion. Yeah, maybe we're going to go, actually, let's click on that. Where will that take us? Here we go. So here we've got our several different ceiling systems. This one is where we've got members that hang under other members. So we'll end up having just a lineal system, so a series of lines. Whereas with this one, all of our members are in the same plane, so we'll end up having a grid system. They can be used for where we've got acoustic tiles, or also in systems whereby you fix plasterboard to the underside of them. So this one here is for plasterboard fixing to it. So you have a suspended ceiling, but then you can plasterboard just like your standard residential ceiling. One of the major benefits of this type of system is it allows a lot of space between that ceiling and the floor above for running services like air conditioning and plumbing and like all this stuff that we can see up here. So that's the benefit. That space between the ceiling and the next floor is called the plenum. So that area where you run all your services, that's called the plenum between those two. Yeah. Oh, we're on ceiling systems already. Yeah, shows us the same thing. So, aluminium grid ceiling system. Trafficable ceiling system, so much heavier sections. Now these sections here, they're cold form, basically they're RHSs, but cold rolled RHSs. Now these cold rolled RHSs have in recent years gotten a lot of use for steel framed flooring for buildings as well. There's a company here in South Australia out at Monarto called Newtech, and I visited them during the holidays. I was interested in some of their stuff for residential building. They produce a whole lot of transportable camps and cabins and things like that for mining services, but they were looking at getting into residential. Unfortunately, they've decided not to, so they're not going to supply their products to the wider market, to builders, but they were looking at doing that. They produce sections like this for doing all their portable buildings with, but it was something I was quite interested in for a build project. But there's still a company in New South Wales that will produce those flooring systems with this, but of course you've got to pay for transport, etc. from there. So that's, what happens if I shrink that down? I need to go back to the Learn site and bring us back to here again. So steel portal frame construction. So can anybody think of where you would see a steel portal frame?
you mentioned the windows, buildings, the facade, glass.
Yes, yep, definitely. So sometimes we'll have a timber building, like a timber framed building, but then we want really big windows in that timber building. One way to achieve that is with introducing a steel portal frame within that timber building, and you see that a lot now within residential construction. You see a predominantly timber frame, but then these heavy red steel sections within the house frame there. That's to create these large open spans, so spans that you can't achieve with timber, even with engineered timber. But it also provides bracing because we've got our columns that are joined to our top rafters, which create a rigid frame, and that provides bracing to the building. So if we look at our timber frame over there, we've got that cross bracing happening on there. Introduce a portal frame, you don't have to have that cross bracing, so you can have a big window in there. If you have to have that cross bracing there, well, you probably don't want to have a window behind the cross bracing. It's pretty ugly or pretty bad detail. So that's a really good use.
Yep. Warehouses.
Exactly, warehouses. So and you see a lot of I see a lot because what I'm doing outside of the TAFE is building large water tanks. So big water tanks on hay sheds and industrial properties, etc. So portal frames all the time for those large sheds. I'll just quickly show you. So portal frame shed, just do an image search of that. But there we go, straight away. This is what we're talking about. Where we've got large frames like this that are joined together we've got some wall girts and then some purlins on the ceiling. Now those portal frames, they'll mount to a concrete structure beneath with that detail that we showed before with the plate fixing and the nuts underneath, the adjustable nuts. And then once it's all set in place, you use a non-shrink grout underneath those plates to keep them rigid, so they don't just rely on the bolt fixing, but they've got a grout bed as well underneath them. So this is what we mean by portal frame construction, but it's not simply limited to industrial buildings, etc. You can also build a whole house using portal frame constructions. Or even domestic sheds, etc. Righty-ho, no, I've lost my place here with portal frame construction. No, that's not the one. Here we are. So portal frames are a bulk active structure, i.e. all load transferred through the bulk of the structural form. Portal frames are made in a variety of shapes and sizes. They are usually made from steel, but can also be made from concrete or timber. Some years ago, I was involved in detailing up repairs for a whole host of buildings around where there was a oil recycling plant fire in Wingfield. Does anybody remember that fire from the news? Yeah, I guess, well, it's flash in the pan, excuse the pun. But it was a very intense fire. As you could imagine, from an oil recycling facility, so they've got cooking oils and all these different types of oils there that they refine and recycle into all sorts of things. They've got a lot of that on site, so a lot of flammable stuff that caught alight. And it was a big place in Wingfield, and all the buildings around that, cars and everything, just got absolutely cooked. So for so many buildings around it, all these warehouses, etc., they got really cooked. Some of the tilt-up concrete warehouses survived fairly well. You've got to have fire of 1200 degrees Celsius before you start doing significant damage to concrete. But still, some of those got damaged to the point of requiring reinstatement as well and repairs. But one building which I found really surprising in how well it stood up to that fire was a building adjacent that oil facility. Now, I guess it all depends on where the oil was and where it was burning as to the intensity of the fire and which way the wind was pushing it as well. But there was this building next to that, which was actually a timber portal frame building. Well, it was a plywood portal frame. So they had these huge, thick sections of plywood making these portal frames, so engineered timber, then with wall girts on that, and then steel sheeting on the outside. So the steel sheeting provided shielding from the fire and a bit of separation between that shield and the timber portal frames. But those timber portal frames stood up to the heat really well. So where you get steel portal frames, they'll get hot and then they'll start buckling and they'll start falling and they get soft and they buckle. Whereas timber, its structure isn't affected by heat. So those timber portals could get really hot and that building maintained its structure. And because it maintained its structure, it maintained its integrity, so the fire couldn't make it into that building. And so it actually stood up really well to the fire. And I found that really, really interesting. Timber portal frames is something you don't see very much, especially engineered timber portal frames. But I guess because they're expensive, but in this instance it did its job. It worked really well. So portal structures, and I think it looks very good. I think possibly if you were to do an interesting residential development, timber portal frames are an interesting thing to go with, as well. I'll quickly do a Google search for timber portal frames. Can you imagine what I'm talking about? Or well, I'll do the search here too. So here, I don't know if that's even, no, that's Buckland Timber UK. That's basically what this warehouse looked like, though, in Wingfield. So these large engineered timber portal frames. So here, once again, large engineered timber portal frames. So it's really quite a, how I say it, aesthetically pleasing form of construction as well. I think it looks quite elegant. But here we've got timber portal frames for a large industrial building, which look like it's going to house a gantry crane as well. So we've got these big rails installed along the sides there. So what's that?
Overhead crane.
Why?
Overhead crane.
Oh, overhead crane. Yeah. Is there a difference between an overhead crane and a gantry crane?
Gantry crane is overhead crane.
Oh, right. Yeah, same. Yeah.
Yeah, that's what I know.
Yeah. Gantry crane is an overhead crane. Yeah. Yeah. But there we go. Some different timber portal frame constructions. And I'll just quickly flick back to this one here. So you don't necessarily just need to use engineered timber, but you can also use sections of timber with steel plate fixings to create those haunches in there, which is a very simple thing to do. Steel plate cut, or you could have two sections of steel plate cut on an angle and then welded, and then holes drilled to produce these fixing plates, those knee joints. Yeah, once again, steel fixing plates here as well. Right. So that's our timber portals. So the portal structure is designed in such a way that it has no intermediate columns. As a result, large open areas can easily be created within the structure. So look at that, great big span. Okay, so we've got some columns here where our portal frames end, but massive spans. And that's why I see these portal frame constructions predominantly for all these hay sheds and machinery sheds, is you don't want to have that interruption of columns everywhere. So, so farmers are putting these up because they can stack the whole thing full of hay without, having to work around columns and things like that. They can drive their semi-trailer in here and they can turn their semi-trailer around inside the shed. That's a fantastic thing. So factories, shopping centres, warehouses, etc. So advantages and disadvantages of steel portal frames. So advantages: the speed and ease of erection. Once it's all manufactured off-site, then it can be tilted up fairly quickly on-site with the use of a crane. Building can be quickly closed in and made watertight. Framework is prefabricated in a workshop and not affected by weather. That is a big issue for a lot of on-site building work, is weather. It's weather dependent. Site work such as drainage, roads, etc. can be carried out until framework is ready for erection. That's one thing I've seen, is a few of these steel portal frame constructions where they've got scissor lifts and whatnot operating in muddy conditions. It's absolute nightmare, because I don't know if anybody's ever seen a scissor lift driving around, etc. But they don't deal with mud very well. They're super easy to get bogged and whatnot. When you're doing your portal frame construction, if you're going to be building through winter time, yes, it's good to get a good compacted hard base happening first, or even your slab happening first if you can. But at least a good compacted hard stand area to go under your base first before doing your portal frame construction. But just because of the machinery that you're going to be using on that site there, telehandlers and cranes and scissor lifts, etc. You don't want like a boggy, muddy site. So no weather hold up during erecting framework, unless you're on a really boggy clay site. Connected together in factories by welding, and site connections should be bolted. Disadvantages: although steel is incombustible, it has poor resistance to fire as it bends easily when hot, and it's subject to corrosion. So
Transporting them.
Yeah, so transporting them is an issue as well. So you have your limitations around width and length. Typically, for things to be easily transported, you don't want them to be more than 15 meters long and more than 3 meters wide, or 2.7 wide. But you can go to 3 meters, or you can tilt things on an angle. But typically, don't want to have pieces longer than 15 meters. That's why they're all manufactured in these sections and then bolted together on site. But also quite heavy things. So you can't just take everything to site in the one load. You've got to have several trucks going there. But if you were to make a frame from timber to do the same job, you'd have a lot of timber involved. Yeah. So there's the transport issues around that as well. So some terminology. So these are our columns here, our portal width. So that's how wide the various different portals are, and our portal spacing. Our portal spacing ends up being our purlin span. So that's our purlins on the roof, our girts on the wall. And this is our girt span for fixing the sheeting to the side. Got our footings. Well, these are called foundations here. I'll call them footings. Foundation is the soil in which it's built. Footing is the lowest element of the building in contact with that soil. And then we've got our rafters, so our columns and our rafters, and we've got the apex joint here and the knee joint here, or the haunch, whichever one you want to call it. Knee joint or haunch is fine. Oh, there we go, knee bracket or haunch, our rafter and our apex bracket, and then our column. Some more frame features. So we've got our purlins happening on here, but then right on the edge there, we'll have a fascia purlin. So that fascia purlin, that will house our gutter or suspend our gutter. So it's going to be a different purlin than the rest of these. So these all might be Zs, and then our fascia purlin will be a C purlin for fixing the gutter too, for example. Also, we need to have stronger beams over these sections where we're going to be installing roller doors. So we have to have a header beam in there for installing our roller door, because we've got different forces acting on that, and these portal frames are restrained by our girts, whereas where we've got these openings, we don't have any girts there, and we can't have any bracing there, so we need these stronger beams in here to help provide that bracing to our portal frames for where we've got our openings. Next, we've got our bracing, and as with any structure, you start with bracing your corners first. So you think about, okay, we've got this many kilonewtons of force acting on that structure. We have to resist those kilonewtons of force. We do that with our bracing. The locations it's going to be most effective are in our corners, and then after our corners, then our end panels for our roof. So between the two end portal frames is where it's going to be most effective. Sometimes with some portal frame constructions, you don't need a lot of bracing in there. You'll only need roof bracing between two portal frames. If that's the case, you choose to put your bracing where you're going to have openings. So if you're going to have big roller doors happening at this end here, like this, you put your bracing in this last portal frame section. But if not, well, here we can see they've put bracing in over top of these openings here as well to assist that, because if there's going to be a weakness in this structure, it's going to be where we've got an opening. So bracing in the corners, bracing in the end panels, and then bracing above openings. And then any more bracing you need spread out equally throughout the frame. Also, so this is an insulation detail. Where's our insulation in that? Our E-therm. Oh, right, so it's really thin insulation. So reflective foil insulation. So you'll typically see that with your portal frame construction. I think if we look out, as we walk out of TAFE here, you'll see the reflective foil insulation in the structure doing the same thing. This does a couple things. Yes, it stops a lot of that radiant heat. So as our roof sheets get hot and radiate heat, it's reflective, so it reflects that heat back up. Some of this reflective foil insulation has air cells in it as well, and that provides some R value to that insulation to resist the transfer of heat. But it also helps provide a secondary skin for any moisture that gets in. So that moisture is stopped from making its way into the building, and it's directed out. So you lap that insulation out into your gutter, and then your other insulation laps in underneath that. So our portal frame base joints, so the legs or stanchions of the portal frame, need connecting at the bottom to a foundation. Here you can see the base joint connected in place. This, I guess, that is a detail I would most definitely not be happy with at all. Yeah. If you saw that on site, I can't even think where I'd begin to deal with that, actually, because obviously your footings would have been designed to take load over this section here. To then place the load eccentric to where the footings were designed to take that load, you've got issues there. But also, you've got your fixings which are cast in threaded rods. Now those cast in threaded rods are going to they're going to be like this, and this is our concrete here, and then they're going to have a bit of a cog on the end of them to stop them being able to be pulled out of that concrete. So these have a huge degree of restraint in them. They can restrain a lot of kilonewtons of force, and there is a lot of kilonewtons of force acting upon these large portal frames, because they're holding a whole roof, and as you get high winds that pour over that roof, it's putting racking forces on there, which is trying to tip the portal frames over. But you also get that uplift as the building works like an airplane wing. With the wind, it's trying to suck it up. And because your portal frames, they might be like 12 meters apart or something, you've got some massive spacings, they end up having huge uplift. They require a lot of restraint. They require a lot of tie down. That can be achieved when we've got our threaded rod cast into our concrete footings with a cog on the end. You can't pull that out. And it's about the strength of that steel. It's about that steel snapping before you pull it out. Unfortunately, you can't get nearly the same pull out strength with a Dynabolt. So Dynabolt, 1.5 kilonewtons of restraint or something like that. It's very little. And particularly, I look at these and go, oh, yeah, M10 Dynabolts, 50 millimeters deep. That Dynabolt, in best case scenario, its strength will be taking out a cone-shaped chunk of concrete with it that's around, sort of that 30, 40 millimeters in diameter and 50 millimeters deep. That's not very strong. And that's best case scenario. So those Dynabolts, yes, they might take a cone of concrete out with them in best case scenario. Worst case scenario is they just pull out. Yeah. So that sort of detail you'd certainly not be happy with if you saw that.
Normally use camset.
Yes, and that would be a much better alternative. So if you are happy with the eccentricity of the forces on that footing, if you go, okay, that's not an issue, just tie down is our thing, that's what you do. You drill very deep holes and then chemset in threaded rod and then do it like that. But but Dynabolts, nah. They just don't have the pull out. So portal frame apex joints. So often those joints are strengthened because there is a lot of force on that joint. As we've got gravity acting on the building, it makes that joint want to flatten out and essentially start tearing the steel from the bottom to the top. So we can have those joints reinforced by gussets in there. So some welded gussets in there with a flange on the bottom. So basically an I-beam that's been chopped into two and then welded on to the bottom flanges of these I-beam portal frames to deepen that joint, make that joint much deeper, make it much stronger, because that's where you got your concentration of forces happening right in the center of that. But also that joint, not only does it have to restrain the pressures from gravity acting upon it, wanting to make it go flatter, it also has when you've got something which is flattening out like that and opening up, it's called a hogging moment. When you've got something pulling in like this, it's called a bending moment. So not only does this apex joint have to resist that hogging moment, it also has to resist the bending moment as you've got wind forces on the side of the building wanting to compact that portal frame. Yes, make the apex go like this. And so it resists forces in either direction depending on what actions are happening on that building at the time. Same for your portal frame knee joints as well. With a portal frame knee joint, actually under gravity loads, what moment is being applied to the knee joints? Is it a hogging moment or a bending moment under gravity?
Bending.
Yeah. No, you got it. Yeah, bending. Yeah. Because as you know, gravity acting on that rafter at the top, it's a bending moment. So when there's wind pushing on the side of it, what is it? Hogging moment. Yeah, it's the opposite. So it's wanting to do this. So again, the knee joint must be strong to support the roof loads and prevent bending. Gusset pieces will be used to increase strength, give greater bolt area to prevent deflection under load. So bracing has to happen diagonally. What is the difference between a brace and a strut? Because strutting can happen diagonally as well. But what is the difference between the two? Bracing works in tension. So if we've got something which is square shaped and then we have a diagonal brace from corner to corner, if we get wind acting on that, trying to elongate that square, well, it tries to pull the bracing. It's stretching the bracing. The bracing doesn't want to stretch. It stops that whole thing from happening. So you can get some wind on the side and that bracing stops it from happening. Following, and I'll draw it up there. Unfortunately, people at home can't see this, but really it's sort of the only way to show it. We've got some bracing like this. Now we've got wind direction from this way. That bracing is being stretched. In the other direction, we can actually remove that bracing and then put in a solid piece of, let's say, timber, something that works well in compression, or concrete log or something like that. That is a strut. That will do the same thing. As the wind forces here, it's trying to make this, this shape instead, like that. But that strut will stop that from happening. So the strut works in compression, the bracing works in tension. Both of them, or in that scenario, are placed in a diagonal fashion. But you can also use struts vertically for imposed loads, like vertically imposed loads as well. So, or for when you say you're erecting a timber frame for a house, you do your temporary strutting and temporary bracing as well. That can happen diagonally. So the way that's done is you produce a frame on the ground, you nail gun it all together, push, 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 and you've got your frame laying there on the slab. You tilt that up. Now you're not going to have your apprentice standing there until you do the rest of your frames. What you do is you get a piece of timber, cut the end to a sharp point, go out, nail it into, or hammer it into the ground, then get a spare piece of timber and fire some nails into that piece in the ground, like this, and then tilt your wall frame up till you've got it vertical. You got your got your spirit level on it. Get it vertical, fire a nail into there. It's strutted in place, and then your apprentice is free to go chopping up some more timber and making some more frames. So that strutting, use it in buildings, but also in the temporary erection of buildings as well. So
bracing, Michael, be using the rods
yes,
and mostly like tightening them.
exactly, yeah. So with your portal frame bracing for smaller scale stuff where you've got 3, 4, 5 meter spacings between your portal frames, yes, you use that steel rod. And the best way, as you identified then, is to have threaded. So you have a right hand thread and a left hand thread, and a turnbuckle in the middle, and you put those rods in place, and then you tighten it up, get it nice and tight. Our fire shed at Montacute, which has just recently been built almost a year ago now, the bracing inside that just sags. So the builders built the place, but they had cleats on the end of the bracing. They installed it, but they can't tension it up because it's cleated at both ends. And so when it's cleated both ends, you've got to get it millimetre perfect. You've got to get it slightly too short, and then screw your bolts in that pull it up nice and tight. Of course, they didn't do that, and so you've got bracing which sags. It does nothing. So in a high wind event, the fire station there is going to buckle, etc., until that bracing becomes activated. So it's got to move a fair bit until the bracing becomes tight. You understand that? Yeah, straight away. So the best way is, like you said, with a thread, a left-hand thread, and a right-hand thread, and a turnbuckle, and tighten it up. But another way of doing it as well for where you've got really big bracing requirements is to use equal angle as well. So sections of equal angle, but like your steel rod bracing, you've got to get your fixing points correct with that. Your equal angle, that's not going to sag. So it's got to be straight, and then you fix it in there, and then as soon as it's fixed in there, because it's not sagging, if you get any actions on there, it gets activated. It's fine. It's just your rod. You've got to be careful with your rod. You don't have cleats on the end of your rod. That's not a good detail. So this one here, not sure, that might be equal angle they use in that bit. You can also use RHSs as well, or SHSs probably. Sorry. So as with any type of framework, stability is important. To help strengthen the framework and prevent movement, diagonal bracing can be used. So here we've got girts, and these girts span quite a distance. And because we've got these girts that span long distance, well actually no, because we've got some sheeting here that requires vertical fixings, we've got our girts and then we've got our fixing channels on that, or cladding rails fixed to those to create that sheeting. And this is really quite a common detail as well, whereby you have portal frame construction, you have Besser block walls for low down, for impact, so people can be driving around forklifts and whatever, smacking into it with pallets and things like that, and they're not going to do a lot of damage to that external skin. They're not going to hit the bracing, etc. And then all of this external cladding happens as a skin on the outside of that building, and your impact is taken by your Besser block walls here. That's a fairly good detail. So these girts can be fixed horizontal or vertical depending on the way the cladding panels are fixed. What's always really important, so somebody will probably come along here and flash over that, so they'll get a flashing on the end of that. But you've got to think about your details, and so it's all well and good to think about, okay, we're building this great big shed, doing our thing, but then if you don't think through your details adequately, you get some messy bits happening. So often the finish of a lower level external cladding panel is with brick or block work, so it creates a strong protective wall for vehicle and fire protection. But we've got to think about all of our finishing details. So what's going to happen here is we'll end up having a right angle flashing over that, probably fixed over our panels, and then that right angle flashing will be cut away a little bit here to accommodate this flashing at the base. That flashing at the base is probably upturned into this, so if any moisture gets in there, it gets sent out through that flashing at the base. So that's the extent of portal frame construction. Does that make lots of sense to you? Could you go out? Well, you probably can't go out and design portal frames, but you can think about design using portal frames. One design I worked with didn't end up getting built. Ended up being a little bit too expensive for that situation, not because portal frames are expensive, but just because of the design ended up being a little bit, larger, and the way that design could happen is larger, etc. All that sort of stuff. But that was using steel portal frames, but cold rolled sections. So cold rolled C sections back to back. So you got these cold rolled C sections, put them back to back, join them with bolts, you end up having an I-beam, essentially. But your steel I-beams, your hot rolled I-beams, quite expensive. So $300 a linear meter or something, for your big ones, quite expensive stuff. Or you probably get it much cheaper, don't you? Well,
I have no idea about
that. Yeah. But it can be really expensive stuff. Whereas your cold rolled sections, much cheaper, significantly cheaper. And so if you can get your cold rolled sections, join them together to create these I-beams that will span certain distances. And for doing that design, I just went to a shed manufacturer and said, okay, this is what we're wanting to do with portal frames. What do we need to do to span these distances and create these shapes? The main reason we were looking at portal frames for that is because we're wanting to do a 45-degree roof for it. The reason we're wanting to do a 45-degree roof is to house an upper level without actually creating a separate upper level, because with the National Construction Code, for habitable rooms, you've got constraints about ceiling heights. And so the only way to produce these upper rooms that meet those ceiling height requirements is to have a 45-degree roof. Or you have a lower pitch roof, but then you create a lower floor in there to create those ceiling heights. And so steel portal frames is a way of going about that, and a cheap way of going about that as well. So that's one application of it in a residential situation. But Tommy, like you identified, you've got the introduction of portal frames for where you want big windows and things like that. So you have your timber frame and you have a portal frame introduced in there. Or I've seen various different residential. I'll go. see what this shows up. Steel portal frames in residential. Well, that's pretty funky stuff happening there. But this is what I'm talking about. So for a massive big window in here, because we'd need bracing in this wall, to do that bracing, we can just use a portal frame to brace it up. Provides that bracing, means we can have a massive window in there, or drive a car in there or whatever. Here once again, that scenario. But you can also, like they've got here, hot rolled portal frame. Okay, so that's going to be expensive. That's not going to be cheap. Your cheaper option would be to have this light gauge stuff welded together. But with your hot rolled stuff, your depths of members can be much smaller, and so you can do slimmer, more elegant walls with that. Something that has a bit of magic to it. But I was hoping, I've seen plenty of residential scenarios also where they've, rather than this sort of gable-ended portal frame type design, just using like square, like boxy shape grids for portal frames, and then filling that all in with cladding. I was hoping to see one of those in here to show you. That's one example of that. So we get basically these boxy grids, and then we can fill that in with panels. Another way to do it, it's a different aesthetic. So that's sort of like a cubist modernist sort of aesthetic. Where did our gable end? So our gable end, that's more of a sort of traditional throwback. What else? Yeah, let me see for residential context. Oh, there we go. That's a bit of a thing at the moment. I think I might have shown some images of buildings like this previously. Have I shown things like that before? So that's not too dissimilar to that place I was looking at doing with steel portal frames, light gauge steel framing, whereby, that's a steeper pitch than 45 degrees. It's a little bit steeper. What is that? Well, it's about 45, isn't it? But that ends up, looks quite elegant, really. Like, you've got a funny detail here, so there's no gutters, or possibly there's no gutters in that, because they'd have to hide their gutters inside their portal frames. It's not going to happen. Oh, yeah, no, really, in all reality, it's not going to happen. So probably don't have gutters happening on this. You could run gutters between your portal frames and run your downpipes within your wall cavity to create something like that if you wanted to have gutters on it. But in all reality, they're probably not using gutters on this. Probably continue their sheets at the top and then bending them, and have mansard caps on their ridges for their sheets, and then continue them down. But yeah, quite an elegant, modern looking building that's actually essentially very simple to construct. The only real complexity here is the size of our glass. So we've got some massive bits of glass in there that would be very heavy and quite expensive. Apart from that, the rest is all pretty simple. So, yeah, over a swimming pool to create those large clear spans, for example. It's a fairly interesting one. Once again, fairly interesting build. So curved rafters for our portal frame. And then we've got some timber portals. Oh, that looks funky. What was that? So I don't know. I don't know what sort of cladding they've got on that. Yeah, interesting. But they're very elegant portal frames as well, aren't they? Like so obviously the failure points are going to be at the apex joint and the knee joints here. They don't have any gussets in there, and they don't actually have any knee joint webbing either. They've got their fixing plates here that act as a web, but often with your knee joints you've got a web goes vertically like this, and one that goes horizontally gives it more strength into that joint there. they don't have that, but it looks very elegant. Yeah. All right, well, I'll leave it at that for tonight.